Subsequent his completion of special relativity in the case of reference frames in uniform motion, Einstein then focused his study on accelerated motion. In a nutshell, Einstein postulated that within an experiment, it would be impossible to tell the difference between being at rest in a uniform gravitational field and being accelerated. He hypothesized this concept by sealing scientists inside boxes under various circumstances of acceleration and gravity. Initiated from the principle of equivalence, by 1915, Einstein completed his groundbreaking new theory, the general theory of relativity, which described gravity in a revolutionary way. By envisioning experiments in accelerated reference frames and coupled with the principle of equivalence to transfer them to gravitational situations, Einstein hypothesized that light, despite having no mass, should follow a curved path in a gravitational field. Even though there was no demonstration of its veracity, by 1919, it had been demonstrated to be true by planetary observations. Moving ahead forward, Einstein theorized that a gravitational field containing large masses or energy would cause distortion in the shape of four-dimensional spacetime, insofar that gravity will lead to a geometrical warping of the effect of mass on spacetime. Essentially, light waves curve around massive objects because of the warping of spacetime caused by the mass. Likewise, when a planet orbits around a star, such as the Earth around the Sun, follows a curved trajectory not because of the gravitational field pulling on the planet, but because spacetime is warped locally around the star. A much more direct path for the planet to take through this distorted region of spacetime is a curved one. Einstein then summarized his scientific model of how mass distorts spacetime, in which physicists labeled Einstein field equations. Physicists utilized the equations to discover that, while in a strong gravitational field, where objects with large mass distort spacetime the most, reality proceeds the furthest from that predicted by Newton. For example, because Mercury is the closest planet to the Sun, according to general relativity, travels along a strong gravitational field or a strong curved spacetime. The orbit of Mercury could not be explained by Newton, however, Einstein's theory of general relativity has accounted for it. General relativity ultimately provided scientific models of the universe's structure, framework, development, and eventual fate. It predicts that the universe must be either expanding or contracting. Prior to the completion of general relativity, space and time were thought of as only an arena in which events took place. Following general relativity, physicists realized that space and time are dynamic entities that can be affected by mass, forces, and energy. In a black hole, for instance, all of the matter is concentrated into a dense point at the center, called a singularity. A singularity produces an infinite distortion in spacetime, a bottomless gravitational well. Any light that passes a boundary called the event horizon near the entrance of this well cannot return. In conclusion, general relativity adequately gauges the universe with strong predictive power. However, it has little to say about the subatomic world in which many scientists believe gravity must originate. This subatomic world is modeled by another great theory of physics called quantum mechanics, which itself has little to say about gravity. There is, it seems, little in common between the smooth, predictable interactions of spacetime and matter predicted by general relativity and a jumpy subatomic world modeled by quantum mechanics, in which changes in energy and matter occur in quanta. A key goal in modern physics is to find a unifying theory, a quantum theory of gravity, or theory of everything, that unites relativity and quantum mechanics and harmonizes gravity with the other fundamental forces of nature. One of the best hopes lies in string theory, covered in a future topic. Most early 21st century theories of everything suppose that the universe has more dimensions than the early observed theory of space and one of time.